Next, we're going to get into part two of predicting products. In this series of examples here, we're only going to focus in on two primary classes of chemical reactions, those being the single and double replacement reactions. Just to summarize the first three reaction types we took a look at, these were, as I consider them, more simple. I didn't say easy, but simple. In a combustion, you're looking for a compound that contains carbon and hydrogen combined with oxygen. If you see those two reactants, the products are always the same: carbon dioxide and water, so simply balance. To simplify your process, synthesis reactions, at least for our purposes, will always be a combination of two elements. All you have to do in those cases, once you recognize it as a synthesis, is predict their most common charges and put those together into a compound. For a decomposition, you have to use the chart that I showed you to predict what products it will most likely form when you write those products down. Now we're going to use the other charts in the packet to predict products of single and double replacements. Now this is, I guess, a very bad example of a single replacement reaction, but it kind of gives you an idea. In this scenario, you see two people together, okay? Frank and a girl named Mary are together, and a guy named Joe comes along. Frank gets left to the curb here. Now, the idea here is Mary is not going to leave Frank for Joe unless Joe is a better option. I guess you could say he has to be ranked higher than Frank for her to leave him. Okay? Now, the reason I use this example is sometimes single replacement reactions don't occur. The first thing you have to understand here is that the element that comes in, that'd be Joe, has to form the same type of ion as the one that it's going to replace. It doesn't have to be identical, but it's got to swap a positive for a positive or a negative for a negative. And the second thing is the single element that enters the reaction has to be higher on an activity list than the one that's already in the compound. Here are a couple examples of element and compound combinations. Now remember, if the element forms a negative ion, it can only replace a negative ion. And if an element forms a positive ion, it can only replace a positive ion. So in this first example, magnesium is the element. Magnesium forms a +2 charge when it forms an ion. The only thing that it can trade places with would be aluminum. Notice their charges are not the same exactly, but they are of the same type. In the second example, chlorine forms a -1 ion, so it's going to have to swap with the fluorine, which is also a -1 ion. Notice I also say possibly swap. We don't know yet. We have to check that activity series. Note I just gave you a little snapshot of what it looks like. You'll want to use the one in your packet. It'll be much easier to read. But the only way that this is going to happen is if the single element is higher on that list than the one it's going to replace. There are only 4 nonmetals on this one. They are listed at the bottom. We're going to keep it simple that way in terms of the changing out of negative ions. So the majority of these single replacements are going to be formed by the swapping out of positive ions. So if you take a look at those two reactions, if I look at that reaction, I have to determine if magnesium is higher than aluminum. If I look at the chart, it is, so that reaction happens. If I take a look then at the chart to see if chlorine is higher than fluorine, it is not. So if you take a look here at the bottom then, I just write the reaction. Note that when I combine magnesium with chloride and I do the symbol charge cross, the subscripts are a little bit different. That's where the balancing comes in. So I have to write those products correctly, then balance. In the second reaction, I just say it doesn't happen. It doesn't happen because it's already in its most stable state. So those are single replacements. When you have a single replacement reaction, immediately know that you have to look at an activity series to complete it. With a double replacement reaction, we're going to be looking for evidence of a chemical reaction. And some of the most tangible ways is to look for the evolution of a gas, or in some cases, the formation of a precipitate. Now, in these reactions, we're going to be looking for specifically something that is a precipitate, which means it will not dissolve in water or water itself. So you're going to take two compounds and we're going to assume that they're already in an aqueous state. What you're going to do is swap the positive ions and correctly write the formulas of the new compounds. Ask yourself, are one of those compounds water? And if not, is one of the new compounds insoluble? This is where the last two charts come in. You're going to look to see if a compound does not dissolve in water, meaning it's insoluble. You're going to have two charts to use. I would suggest using the table that says 11.6 at the top first. It's probably the simpler one of the two. The reason I provide you with two is no single chart includes everything that you're ever going to need. When they state exceptions, they might say all sulfides are insoluble except those of the 1A and 2A elements. What they're saying are groups 1 and 2, respectively. So here are three examples of reactions. Notice I put the phases in. Those phases indicate that they are already dissolved in water. And so I'm going to take these one at a time. Now, in the first reaction, I've got aluminum nitrate and sodium carbonate. Sodium carbonate is soluble in water. So what I'm going to do is swap the sodium plus 1 with the aluminum plus 3 and write the compound formulas correctly to begin with. Of those two compounds that are formed, neither one is water. So now I have to check the solubilities. So I'm going to look up carbonate and nitrate on table 11.6. It says carbonates are insoluble on that chart. And it states a couple exceptions, but aluminum is not one of them. That means that aluminum carbonate will form a precipitate, which is a solid. Sodium nitrate, all nitrates are soluble without exception, so that'll remain aqueous. So all I got to do then is note which one is my precipitate, that's aluminum carbonate, and then balance, and I'm done. Here's the second reaction. Calcium chloride and sodium hydroxide. Now, the first thing I'm going to do is swap the sodium plus 1 with the calcium plus 2 and write the formulas of those compounds correctly. Remember, hydroxide is polyatomic, so don't forget your parentheses. There's no water, so I got to check the solubility. All chlorides are soluble, and sodium is not one of the exceptions. Hydroxides are all insoluble, but calcium is an exception, meaning that calcium hydroxide is also soluble. Neither one of those products is water. Neither one of those products is insoluble. That reaction doesn't happen. The last one, sulfuric acid and calcium hydroxide. If I swap the calcium plus 2 with hydrogen plus 1, I form calcium sulfate, but notice how I wrote water, HOH. That just makes it easier to balance, but that is water. I don't have to check a solubility chart at this point. I can if I want to for the other product, but I don't need to. Because water forms, this reaction happens. So all you got to do is balance and you're done. Now, some of you may ask yourself, why is it that some of these reactions don't happen? I'm going to show you net ionic equations in the next phase here, and that'll explain this a little bit better. I hope this helps. Try some of those practice problems, and I hope to see some of you on Wednesday for a better explanation. Good luck, and we'll